Hello, I'm John Andrew Havellana, and in this video, we will solve problems related to heat of mixing. This is under Day 2 or Chemical Engineering Principles of the Chemical Engineering Board exam, specifically under C2 Solution Thermodynamics Applications. So for our question, a 28% sulfuric acid solution is to be produced from a 98% sulfuric acid solution and pure water in a continuous flow steam-heated kettle. The 28% acid exits at 65.6 degrees Celsius, and the feed consists of the 98% acid fed at 0 degrees Celsius mixed with water at 21.1 degrees Celsius. Number 4, calculate the amount in kilograms of pure water needed per kilogram of the initial sulfuric acid solution. Number 5, determine the heat added in the kettle per kilogram of the initial sulfuric acid solution. Number 6, if the mixing process were adiabatic, what will be the temperature in degrees Celsius of the kettle effluent? As preparation, we need to first look for the enthalpy concentration diagram for a ChE sulfuric acid at 1 atm. If you are using the 9th edition of the Paris Chemical Engineering Handbook, it is figure 2-18, while for the 8th edition, it can be found as figure 2-31. The units on the axis of the enthalpy concentration diagram, for the y-axis, we have BTU per pound, while in the x-axis, we have the weight percentage of H2SO4. The isotherms or the constant temperature curves here are in degrees Fahrenheit. Since our problem is in SI unit, while this figure is in English units, we need to first convert the energy and masses respectively. In addition, helpful conversion factors for energy is 1 BTU equal to 1054.4 joules, or 1 BTU is 1.055 kilojoules. And this can be found respectively in the 9th edition, table 1-6 for energy, and for 8th edition, table 1-4 for energy and work. So for the first question, number 4, calculate the amount in kilograms of pure water needed per kilogram of the initial sulfuric acid solution. So this first step is a type of material balance. So consider that our kettle is represented by this box, and we are mixing 98% sulfuric acid and pure water, exiting as a 20% sulfuric acid. So our basis here is per kilogram of the initial sulfuric acid solution. And this initial sulfuric acid solution is the 98% sulfuric acid. So as our basis, we can write 1 kilogram of 98% sulfuric acid. So since the sulfuric acid is being diluted by water, this amount of sulfuric acid will not change. The concentration will decrease, but the amount of sulfuric acid molecules, for example, is constant. So in this case, you can write 0.90 of this 1 kilogram solution divided by its total mass at the exit, 1 kilogram of 98% sulfuric acid plus the water that is added to dilute this sulfuric acid will give us the 28% sulfuric acid, which is 0.20. So the numerator here gives the amount of the pure sulfuric acid present in the 98% sulfuric acid, while the denominator is the combined amount of this initial acid and the water used to dilute it to 28%. So from this equation, this is one equation, one unknown, and we can solve for mass of the water. So we can calculate MH2O is equal to 3.5 kilograms. From the choices, this is letter C. Next, for question number 5, determine the heat added in the kettle per kilogram of the initial sulfuric acid solution. So we have calculated from the previous problem. Suppose this is our kettle. We have 1 kilogram of 90% sulfuric acid and its temperature is 0 degrees Celsius. We can convert this to English units as 2.2 pound mass of 90% sulfuric acid and 0 degrees Celsius is 32 degrees Fahrenheit. The other stream of our feed is water. We have calculated that we need 3.5 kilograms of water, and this is fed at 21.1 degrees Celsius. Converting our water stream, 3.5 kilograms of water is equivalent to 7.7 pound mass of water, 21.1 degrees Celsius is equivalent to 69.98 degrees Fahrenheit or approximately 70 degrees Fahrenheit. For our exiting stream, adding these masses, we will have 9.9 pound mass of 20% sulfuric acid, and it is given that it will leave at 65.6 degrees Celsius. 65.6 degrees Celsius is equivalent to 150.08 degrees Fahrenheit or 150 degrees Fahrenheit. Since we do not know yet if this process is adiabatic or not, we can represent the amount of heat added as Q, and this will serve as the figure for our energy balance. Next, we need to read values of enthalpies of all the stream from the enthalpy concentration diagram. So we need to represent their enthalpies as follows. Let's denote the initial acid stream in terms of masses and enthalpies, M1 and H1. For the water stream, let's denote that as M2 and H2, and for the exiting stream, let's denote that as M3 and H3. The energy balance for this problem given by M1H1 plus M2H2 plus Q equals M3H3. The left side of the equation represents the incoming or input of energy into the system, while the right side of the equation indicates the energy of the leaving stream. Currently, we now have the values of M1, M2, and M3, or the amounts in terms of masses. And what we are required for question 5 is this Q. So we now obtain the values of the enthalpies of H1, H2, and H3 from the HX diagram. From the HX diagram, we can determine that the enthalpy is a function both of composition, X for the weight percentage sulfuric acid, and temperature. And for all the streams, we already have the composition and temperature. So next, in the next slide, we'll read the values of the enthalpies from the figure. So first, for M1 and H1, our initial acid is 98% at 0 degrees Celsius or 32 degrees Fahrenheit. So this is 90% sulfuric acid, and this is 32 degrees Fahrenheit. So the curve here represents this temperature. So we read the value here for H1. And H1, reading from the y-axis, this is slightly above negative 80. So let's assume H1 is approximately negative 79 ATU per pound mass. For the second stream, or that of pure water is 0% sulfuric acid, which is here in the diagram. And the temperature of water is 21 degrees Celsius or approximately 70 degrees Fahrenheit. So this is 0% of H2SO4, and this is 70 degrees Fahrenheit. So this is the curve, and we intersect it at this side. This is slightly below 40. So let's denote H2 as approximately 39 BTU per pound mass. And lastly, for our exiting stream, it is a 28% acid, which is here, and it exits at 650 degrees Celsius, or in degrees Fahrenheit, it is 150 degrees Fahrenheit. So we read from this curve at 28% sulfuric acid and read from the y-axis. So this is slightly below the value before. So this is H3, approximately around 37.5 BTU per pound mass. Substituting these values to our energy balance, we can now obtain the amount of heat added in the kettle per kilogram of the initial sulfuric acid solution. We now go back to our energy balance. M1H1 plus M2H2 plus Q equals M3H3. So our M1 is the basis initial sulfuric acid solution of 1 kilogram or 2.2 pound mass. H1 is negative 79 BTU per pound mass. For the next term, M2H2. So M2, the amount of water, is 7.7 pound mass. H2, enthalpy of water, is 39 BTU per pound mass. And our currently unknown Q. This is equal to M3H3, where M3 is 9.9 pound mass and H3 is 37.5 BTU per pound mass. So this is one equation, one unknown, and we can solve for Q. So solving, Q is approximately 244.75 BTU. This is based on a 2.2 pound mass initial acid. Since our choices and problem is in SI unit, we need to convert this. So 2.2 pound mass per kilogram. We will cancel LBM. Next, we convert BTU, multiplying 1.0544 kilojoules per BTU. We can cancel BTU, and our answer is in kilojoules per kilogram. So calculating Q is approximately 258.0644 kilojoules per kilogram. So this answer is nearest to the choice letter B, 256 kilojoules per kilogram. The slight difference is due to the graphical technique, and there are errors associated with reading the values from the graph. Lastly, for question number 6, if the mixing process were adiabatic, what will be the temperature in degrees Celsius of the kettle effluent? So we are given 40, 50, 55, and 45 degrees Celsius. So from our original energy balance, if the process were adiabatic, then we simply set Q equal to 0. So our energy balance becomes M1H1 plus M2H2 equals M3H3. Since the process becomes adiabatic, we can assume that the exiting temperature is slightly lower since there is no input of heat from the environment. And since the temperature of the exiting stream will change, therefore its enthalpy will also change. So let's denote its new enthalpy as H3 prime. Substituting the previous values to the original equation, can have M1H1, so this is 2.2 pound mass times H1, which is negative 79 BTU per pound mass, plus M2H2, so plus 7.7 pound mass times 39 BTU per pound mass, and their sum is equal to M3H3 prime. M3 is 9.9 pound mass, and currently our unknown is H3 prime. So from this equation, we can calculate H3 prime. The value of H3 prime can be calculated as around 12.77 BTU per pound mass. So now that we have H3 prime and its composition is 20 weight percent, we can read from the graph regarding its temperature. So read from the enthalpy concentration plot. So we have H3 prime around 12.77 BTU per pound mass, and the concentration is 20 weight percent. So in this figure, the x-coordinate is in terms of 20 weight percent sulfuric acid, and approximately from the y-axis, this is 40 BTU per pound mass, and this is around 20 BTU per pound mass. So 12.77 is somewhere around here. So the intersection is this point. So since it does not fall on any of the isotherms, we need to approximate its temperature. So we can see from the plot that it is between 100 degrees Fahrenheit and 150 degrees Fahrenheit. We can somehow approximate an isotherm that passes through this point. Since it is somehow in between 100 and 150 degrees Celsius, then we can approximate the temperature as around 125 degrees Fahrenheit. And if we will convert 125 degrees Fahrenheit, this is approximately 51.6667 degrees Celsius, or this is nearest to 50 degrees Celsius. So from the choices, the correct answer is letter B, 50 degrees Celsius. So that's it for our discussion on problems related to heat of mixing. If you enjoyed this video, please like and subscribe. See you in our next video.